Today's topic, again, is planning for your simulation project. Okay, and just to give you an idea of what we're going to be covering today, we're going to be talking about making a roadmap for your simulation project. And really what we find the best way to start any simulation project instead of just diving in head first is really to ask yourself some questions. In particular, there's 8 questions that I'm going to sort of highlight, and we'll talk about how this can really help shape and plan your analysis before you even really get into the software. We're going to then take those questions and we're going to take a look at a case study that we did for one of our customers and see how those questions apply to their particular analysis. So just to give you a little background on myself and my panelist, Jared, we've been working in Hawkridge for a little while. We've combined about 14 years we've been working here. And most of the time we've been spending our time working on the simulation or Cosmos end of things. And in particular, both myself and Jared work in the simulation services department. And with simulation services, we really offer analysis consulting. We offer custom training as well as one-on-one mentoring sessions. Okay? And one of the things that I've gotten out of teaching these mentoring sessions and the custom training as well is this idea of planning your analysis. So when we teach a mentoring session in particular, we start by teaching about planning your analysis, then we talk about simplifying your model and prepping your model, and then we finally talk about setting up the analysis and then running it. But really everything starts with planning your analysis before you even get into the software. And when we talk about planning, it's just like if you were going to take a road trip and you wanted to figure out, okay, we're at point A, we're going to go to point B, and we need to figure out how long it's going to take to get there, any pit stops along the way, what route are we going to take, that type of thing. It's the same thing with analysis. Before you even start your analysis, you really want to plan out where you're going, how you want to end up, and what steps you're going to take to get there. And so the best way we found with our mentoring services is teaching customers to really ask and answer several different questions, and not just ask these questions, but really write them down and refer back to them from time to time. It really helps you focus your efforts when you're doing an analysis. So let's go ahead and let's start planning our analysis. What's the first question that we ask when we're planning an analysis? Well, probably the biggest question is, what the heck's my end goal? Why am I doing this analysis in the first place? Is it because I want my product to be stronger? Do I want to remove some material because maybe it costs too much currently? Do I want to make it lighter? Do I want to make it faster? Am I doing some sort of electronics box and I need to make it cooler? Maybe I need to make it hotter, right? What is the end goal? This is really the question that you want to ask yourself and really frame your analysis with. And, by answering this question, you're going to be able to dictate what kind of analysis or analyses you need to run, what kind of outputs are you going to need? Is it stress? Is it frequency? Is it displacement? Is it response? It's going to answer a lot of questions just by answering this one, what is my end goal? So, once we figured out what our end goal is, well, what do I need to get there? What outputs do I need from the software to actually achieve that end goal, to make it lighter, stronger, faster, cooler, whatever it is? Well, do you need stress numbers? Do you need displacement? Do you need temperature? Do you need to know how the structure responds? Based on what outputs you require, really that's going to tell you then, okay, what do I need to run? What kind of analysis do I need to run? Is it going to be a static analysis? Is it going to be a dynamic analysis? Is it going to be a frequency analysis? Answering this question will frame question 3, which is, which analysis should I use? So, I put our little matrix here, and you guys might have seen this before whenever we do a presentation about simulation or sales presentation about simulation in particular. We show you all the different modules that we have. You show you Simulation Professional that has all these tools like static and thermal drop test, or we can go into flow simulation and look at CFD. But really, the bottom line is there's a lot of different tools available to you, but oftentimes you're not really sure which analysis you actually want to run, right? Do I want to run a static analysis, maybe a nonlinear analysis? How do I choose? Well, we've already figured out what our end goal is. We've already figured out what our outputs that we need, if it's stress or displacement. You know, should I use a linear versus a nonlinear analysis? Well, looking at the difference between the two, you know, do you have a nonlinear stress strain curve? Is contact a big issue? During your loading condition, is contact going to be a problem? Are you seeing large deflections? You know, answering these types of questions are going to let you know, hey, do I run a linear analysis or do I need to run a nonlinear analysis? Most oftentimes, you probably want to run both just to see. You know, if you want to run a nonlinear analysis, what we often suggest is, you know, start with a linear analysis first. And then once you've gotten your feet wet with a linear analysis and, you know, you've looked at the answers and they look about, you know, what you'd expect, then you can move on to a nonlinear analysis. You know, maybe you're stuck between, is it static? Is it dynamic? Well, we often ask the question, well, you know, does the speed of the loading matter? You know, are you loading it really, really fast where you have these inertial effects involved, or can you assume that you load it really slowly and you don't need to worry about inertial effects? You know, are you looking for the response of the structure, or are you just looking for that equilibrium final stress or displacement? You know, for a lot of our electronics cooling customers, you know, they often ask us, you know, should I use our flow tool or should I use the Sim Professional thermal module, right? That's always a question that gets asked. And what I pose to them is, well, do you know your convection coefficients? Is the fluid flow around your model, is that going to be of a big concern? Is that something that you're not really sure, you know, what's happening there, or maybe you don't know the convection coefficients? Then maybe you should do a flow analysis. If you do know those, and maybe you're working in an environment, say a vacuum, and there's not really any fluid there, maybe thermal would work better for your case. Bottom line is, you know, for what analysis you should use, it's going to depend on the loading conditions you have and really answering those first two questions. What is my end goal, and what outputs do I need? Okay. So the fourth question that we ask when we're planning an analysis is, you know, what model should I use? And this is a question that I'm surprised not as many customers ask, because it seems like a really simple question, right? What model should I use? Well, it's the model that I designed, right? The model that's in the real world. Usually the question we get, or the answer that we get. And oftentimes when we have our CAD model and we've either gotten it from a designer or you are the designer and you're just setting it up for analysis, you designed it with manufacturing in mind, right? You're going to build the model, you're going to build your product, and in the CAD world it looks exactly like what it would look like in the real world. Well, in analysis, oftentimes you don't want to use that full detailed model right off the bat. You know, you're going to run into a lot of headache. It's going to be hard to troubleshoot if you start with all the details and then try to figure out what's going on. Ideally, we'd like to start with a simplified model and then sort of add detail as we go. We can start relatively simple, pretty simple, and then if that's a little too simple, we can add a little more detail, add some more components if necessary, and then work up, right? So, you know, most of you have probably heard of this, you know, start simple, but the question then becomes, do I start with my existing model, my CAD model that I've designed for manufacturing, and simplify it, maybe make a configuration, make a copy of the part, and then get rid of some fillets, get rid of some extra components, some holes, things like that, and whittle it down? Or would it just be easier to create a brand new model from scratch and then just build your simplified model and be done with that? You know, I've actually seen it both ways when when we're working with customers in our mentoring sessions is we'll have some customers that they have a pretty good model. It's pretty easy to simplify. If you suppress 3 fillets, it doesn't break all of the features in the entire tree. In that case, it might be easier to work with the existing model. But there's some times where you have a really complex model, pretty hectic, what's going on with lots of components and lots of features. It might just be easier to just cut your losses, start from scratch, and then build up from nothing, essentially. So that's a question that definitely should get asked when you're planning your analysis. So now we've sort of done this a little backwards. We've asked for outputs first, and now we're asking for inputs second. So, for my 5th question, what inputs am I going to need? And it's really good before you even get into the software and start pushing buttons to gather as many inputs as you possibly can. For a lot of different analyses, you're going to want sort of the same inputs. You're going to need material properties, pretty much regardless of what analysis you're going to need to run. You're going to need material properties. You're going to have some idea of the loading conditions. Is it going to be force or pressure? Is it going to be 200 pounds, 400 pounds, a ton? Is it going to have 50 watts of input, etc.? Those are really good to gather up front and before you actually go into the software. But the other question that you should ask is, how many of these components in my model can I remove? Maybe I can simplify. If I can turn them into fixtures or remote masses, remote loads, it's almost like you're planning your model simplification before you actually simplify your model. The other question that I often forget about, and I have to make it a point to remember to ask, is, can I leverage symmetry? Right? Symmetry is often a tool that we forget to use because in real life, it's not cut in half, or it's not cut into a quarter or an eighth pie, right? But in the software, you can really cut down on the solve time, the meshing time, if you realize that, hey, my model's actually symmetric, the loading conditions are symmetric, maybe I could take advantage of half symmetry, quarter symmetry, and make a note of that before you actually go into the software, because most likely your manufacturing model is not half of your product, right, or a quarter of your product. You might need to make a configuration that is a half model or quarter model. So, the 6th question that we ask, and it's something in services that we actually write down in our statement of work because it's really important to us, is what are the assumptions that we're going to make? What's the big deal with assumptions? Well, understanding the assumptions that you make in an analysis are really going to help you understand the results that you get. Now, every analysis is going to have some sort of assumption. Even if you have all of the details in your model, the loading conditions, the boundary conditions, they're going to have some sort of assumption built in. Some generic assumptions that we often come across, manufacturing defects aren't considered. So what are we saying here? We're saying that our assumption is everything, all the metals, all the plastics are perfectly made. There's no cracks in them, no manufacturing cracks. All the welds that may be holding the thing together are perfect welds. The welder had a really good day at work and he didn't mess up anything. All of them are the correct size. So we're not even considering manufacturing defects. One of the things that if we run a thermal analysis with our thermal module is we say that the convection coefficient that we specify is going to be uniform across the entire face that we've specified it on. Now, in real life, that might not be real, right? In real life, the convection coefficient may be different at one end of the face than it is at the other. And, for this assumption, you have to understand that assumption. So when you get the results back from your analysis, you can understand the results that come out of it. To give you a little example, if you make an assumption about a material property, you say that your material property, you don't really know the exact numbers, but you're just going to input, a elastic modulus, a Poisson's ratio, and then you run the analysis and you get your stress, your displacement numbers back, and You look at the displacement and you say, wait a minute, our displacement is not as much as we see in real life. Why is that? If you give those results to your boss, you give it to your customer, and they come back and ask you that question, well, if you understand the assumption that, hey, I put this material property in, it's not the exact material that we used, and the material that we use is actually stiffer than what's happening in real life, that's why we're seeing the displacements that we see. That's why we're seeing the stresses that we see. So again, understanding the assumptions that you're making is really going to help you understand the results that you get out of the software. So the seventh question that we ask is, what kind of accuracy am I looking for? We ask this question and we almost always get this answer. I want it to be as accurate as possible, no questions asked, right? I want it out to 5, 6 decimal places. It's got to match what the real world gives me. This isn't always the most realistic way to look at an analysis, just from a time perspective even. And when we in services, we look at accuracy, we look at it with sort of two ends of the spectrum. We have matching exact values with the real world, and then we look at trends, which is sort of the other side of the spectrum. Let me explain that. So, from one end of the spectrum, matching exact results, it requires a lot more detail. If you want to exactly match what you're seeing in the real world, you're going to have to include more details. You're going to have less assumptions. So you can't have as many assumptions as you may like. And all of these things are really going to equal more computational time. Not even from a solving standpoint, but from a geometry simplification standpoint, a troubleshooting standpoint perhaps, it's going to take more time. Looking at trends is really, the idea behind looking at trends is you're looking for a reasonable value. It doesn't have to be exact out to 3 decimal places, but it's a good, reasonable value that you get for a result. But the idea behind it is you want to take that model and then make a design change to it. And really what you're interested in is seeing if that design change helped your cause, helped your design, or harmed your design, right? And so you don't really care so much about the exact numbers as much as, if I make this change, is it going to help or hurt my design? And if you're looking at trends that way, you don't need as much detail in your model, so you can get away with a simpler model. You can get away with more assumptions. And all of this sort of adds up to less computational time. You can get your project done faster, and really the result that you're after is, I'm trying to improve my design. And oftentimes, after talking with customers about these two types of accuracy, what they start out with is wanting exact values. And by the time we're done with the phone conversation, they really are looking at the trends, right? They're looking at how my model is going to behave once I make these design changes to it. So the last question to frame your project and really get a feel for what your project is where your project is going is, how do I know my results are going to be correct? I've talked to our tech support team. They get this question a lot. We get this question a lot. How do I know it's correct? Well, there's really two things to blame if you get a result back that you don't expect or you think is wrong. Really, there's two things. One, the software is acting up. It's not reporting the numbers back correctly. There's something wrong with the software or the solver or the method it's using. The other thing to blame would be the input or the geometry, right? Remember, everyone's heard of the term garbage in, garbage out, right? So, unfortunately for our customers, what we've found is that 98, 99% of the time, the software actually isn't to blame. It's something about the input not matching what you see in real life. We at Hawkridge and also SolidWorks, we have validation tools, NAFEM's validation tools, within the software that if you're curious about how the solver stacks up against hand calcs or the sort of academic analytical problems, we do have those available in the software that you can take a look at, and you can see what the hand calc is for a particular problem, and then you could see how SOLIDWORKS simulation runs that problem and what the results it gets or gives to you. And we've looked at a lot of different problems over the years, and we've found that the solver's pretty good. It's pretty robust, and most of the time the error comes from the input, whether it's a bad material property, maybe it's not exactly what you're seeing in the real world, it's a bad boundary condition, maybe a fixture isn't appropriate, or maybe an assumption that you've made about your analysis isn't appropriate. So what we often like to say is, well, how do I know my results are going to be correct? Well, what's your validation method? Do you have any previous analyses that you've run? Do you have a field result? Maybe your field engineer came back and told you, hey, we loaded it up with this condition and it failed. This was all the data that we got from the field. Or maybe you have a napkin hand calculation or some Excel spreadsheet, that'll give you a hand calculation. So the bottom line is have a validated result before you go into your analysis. So you have something to compare with. And if you don't have that, at least have a ballpark idea of the numbers you'd expect to get, so you know whether you've actually got a good analysis start or not. So those are actually the 8 questions that we frame when we do a mentoring session and we plan out a customer's analysis. Now, I'd like to say, a quick thanks to Marathon Industries. I got their permission to use their case here that we did for them. And really, their analysis was dealing with a plastic wheel. So to give you a little background on Marathon, Marathon is a company up in Washington, state of Washington, and they make plastic wheels for various applications. They make them for wheelbarrows, and they make them for hand trucks and carts and things like that. And they are an OEM supplier, so they make a whole bunch of these wheels at a time. Customer calls them up, we need 1 million of your plastic wheels. So it's large volume. And what they were after, really their end goal, if you will, was to see if they could remove some material from one of their wheel designs, but maintain the strength of their wheel. All right, so because they're making so many of these wheels, if they can remove maybe 0.5 gram or a 1/4 gram of plastic from their wheels over 1 million wheels, they're going to save a lot of money. Right? So Marathon came to us with this problem, and they had the software, they had SOLIDWORKS simulation, and they wanted to know, hey, we want to solve this problem, but we want you, Hawkridge, to teach us how to do it. So they attended 2 of our mentoring sessions, and we went through their problem and we discussed, how to approach their analysis. So just like what I did with Marathon, I'm going to walk through with you guys real quick and answer those 8 questions with their analysis. So what was their end goal? Well, plain and simple, with an existing design that they had, we want to use less material, save on a little bit of material, but keep the strength of their wheel, right? Again, they fulfill large orders of wheels, so any weight savings that they do is going to save them a lot in the long run. All right? Okay, well, what outputs are they going to need? Well, they're primarily interested in high stress, or in the other case, low stress. Really, they're looking to remove material, and so what they wanted to do was they wanted to look at their wheel, and they wanted to see, okay, wherever the areas that don't see a lot of stress, where maybe the load path isn't located, let's see if we can remove some material in those areas and see if that really altered our stress at all, altered our factor of safety. And if it didn't, hey, we can remove some material there, we'll be perfectly fine. So, then they said, okay, well, what analysis are we going to need? Well, we looked at their problem and we said, well, what are our assumptions? Can we say the force could be applied slowly? They said, yeah, we can assume that. Is your plastic material, are we going to yield it? Is it going to behave in some exotic fashion? They're like, no, we're going to say it's going to behave linearly. And really what they were after was the stresses, and also they wanted to see what kind of displacement or deformation it did under the loading conditions. So, with these ideas in mind, what would you guys think? Static, dynamic, probably not a flow analysis, right? So our first thought was, okay, what about a linear static analysis? Well, what we ended up doing was we actually started with a linear static analysis, and then we went to a nonlinear analysis. And the reason for that is they wanted to test their wheel acting on the ground, and they wanted to see what happens as the wheel deforms, while it's in contact with the ground, what happens to it. And so that's a nonlinearity of this changing of ground contact between the wheel and the ground I wanted to look at. And so we said, okay, well, that's going to be a nonlinear problem. But since we're doing 2 mentoring sessions, let's start with a linear analysis. Let's get our feet wet, make sure we're good with a linear analysis, and then we'll proceed to a nonlinear analysis, right? So what model did we end up using? Well, let's actually take a look, before I actually get into why, and let's take a look at their model and see what I saw. So I'm going to bring up SOLIDWORKS here, and this is their wheel model that they gave us. So if we take a look, this is the non-simplified model they sent us. It's got all the fillets in it and all the cuts. We look at it and we say, okay, it's got some detail in it. But in looking at this model, the first thing I thought of was, should we use solid elements or should we use shell elements? Well, if we look at this if we wanted to do shell elements, and again, a little background, shell elements are really good for thin-walled structures that have uniform thickness. And in order to use shell elements, we either need to make the component into a sheet metal component, or we need to make some surfaces that we can use as our shell faces. Are 2 typical ways that we can turn this into a shell problem. But in looking at this, it's pretty complex. If we look at some of the wall thicknesses, they're not all uniform, especially in this area. So, what we ended up doing was we said, okay, well, let's go with solid elements to start and see how far we can get with solid elements. And so because we decided to go with solid elements and there wasn't too many features that we needed to remove, we decided, hey, let's go with the customer's model. We didn't have to start from scratch and build this up. Now, if we did use a shell type model for this analysis, I might second guess that and I might want to build it from scratch to use a shell type model. But we ended up using their model anyway. So what were the inputs that they needed? Well, they were looking at a 200-pound load, and they wanted to look at primarily the wheel. There's a tire associated with this wheel, but they didn't really care so much about the tire. Their main concern was the plastic wheel itself. And they told us that the wheel, there's a tire on it, and the wheel is attached to an axle by 2 bearings. There's 2 bearings on there. But we really don't care about the axle. We really don't care about the bearings or the tire. So how would we set this up? Well, we take all that information and we try to envision, okay, how are we going to do this in terms of fixtures and connections and loads? Well, because they told us the tire, they didn't really care so much about the bearing or the axle. We said, okay, well, we can remove those. We can save all of our meshing time by removing those, and we can add fixtures to it. So what we did was we added a bearing load to represent the force where the axle meets the wheel. And for the ground, we said, well, we're assuming that the ground is much more rigid than the wheel was. So we made a surface and we said, hey, this is going to be a perfectly rigid surface. That was a good assumption. And the other nice thing is because this wheel, the way it was oriented, was symmetric about the right plane, we decided to cut the model in half and use symmetry about the right plane. So just to show you guys what we ended up using, this was the model that they gave us right off the bat, and this was what we ended up using for our analysis. So we cut it in half about the right plane, and we added, see that little surface down at the bottom? This is actually what we ended up analyzing. So I can show you. We simplified it a little bit. We still kept some of the fillets in there because we found some of these fillets were needed structurally. But we removed as much cosmetic as we could and added some symmetry. So what are some of the assumptions that we made with this case study? Well, we said that, this wheel is going to experience some small deflection. Okay, so we're not saying that this thing is going to compress 50%. We said that the wheel material is going to behave in a linear elastic fashion. It's not some exotic material that we have to worry about. And the way we're loading it, we don't have to worry about inertial effects, right? So to give you an example, if we were going to try and simulate someone taking this hand truck that has their wheels and dropping it off of the back of a pickup truck or maybe off of a curb onto the ground, that's going to represent sort of a sudden impact instead of a nice slow loading condition. In that case, we wouldn't be running a static analysis. We'd be looking more at a dynamic type of analysis. But for this case, we're just saying we're just going to load it slowly with 200 pounds. We also made the assumption that the ground that we had is much more rigid than the wheels, so we could just say, hey, it's a perfectly rigid surface, and that's why if you looked at our model, just had a perfectly rigid surface there. And we didn't worry about gravity. We said, this model's small enough, and gravity effects compared to the rest of the loading conditions are not going to be considered significant. So just a few of the assumptions that we made and we actually documented for Marathon. So what kind of accuracy did we end up looking at? Well, for this one, remember, we can either look at one end of the spectrum and look at matching exact results, or we can look at trends. And for Marathon, what we did was we actually looked at the trends. It sort of fell closer to the trend side of the spectrum. Because remember, what was our end goal? Our end goal was to remove material and see if we could keep that strength there, right? So it doesn't really matter what the exact number is, as long as if we remove material, our stress values, our factor of safety doesn't change very much, and that's really looking more at trends. So, I asked Marathon when we got their model, say, we can run all of these analyses, but how are you guys going to know that what I give you or what I show you is going to be even ballpark what you expect? Well, the nice thing, we actually got the timing right, was they had told us, we have similar wheels out in the field, and so we have an idea what's going to happen with our wheel. They told us they typically over-design their wheels because they haven't in the past used analysis tools. They've simply said, okay, we'll just throw a whole bunch of plastic at it, and it's not going to fail. And they've told us they haven't had any field failures with their plastic wheels. But the issue with just throwing more plastic at it is that they're sort of brute forcing the design, right? They're not optimizing where maybe you can remove some material here. It's not really going to make much of a difference and save them some money. So they told us that they had wheels in the field, that they had a ballpark idea. But even better was they had mentioned to me during the mentoring sessions that they had just sent out these wheels that we were looking at, the current design for prototyping, and they were going to get a couple of those back soon, and they were going to test them in the lab and put them under the same loading conditions to see if they can get a correlation. So with Marathon, their validation method was lab results and field results rather than hand calculations. So, with planning your analysis, really, instead of just jumping in to your analysis, it's really crucial if you want to have consistently successful results, to plan before you go ahead and start clicking on buttons within simulation or flow simulation. You know, I've posed these 8 questions, and you know, if you take one of our mentoring sessions, we'll take your problem and we'll look at these 8 questions with you. But answering these 8 questions really is going to define the scope of your project and really keep you on track, not let you go off onto little analysis tangents, and before you know it, you'll have no idea where you started. The other thing that I find key is don't just ask these questions or answer them. Keep track of them. Write them down. If it's Notepad, put it, post it in your cube, put it in a PowerPoint presentation. Just keep a record of the answers to these 8 questions and refer back to them from time to time, so you can always go back and see what's the end goal that I'm asking. What are the outputs that I need? Have I changed the scope since I first started this project? Do I need to alter my goal at all? Keeping track of this is really key to running successful analyses consistently. So for February, we just talked about planning for your simulation project. Today's the 19th. A little bit later today at 3 p.m., we're going to have an e-demo about SOLIDWORKS Enterprise PDM. If you're ever curious about Enterprise PDM or product data management, and you want to know how that can help you with your data management, tune in at 3 p.m. We have a webinar on that. And then on the 26th, next week, the Wednesday, we're going to have an e-learning session on SOLIDWORKS Electrical and about wire management. So if you're curious or you've used SOLIDWORKS Electrical and you want to know more about wire management, in particular wire styles, tune in for that at 11 a.m. And then on the 26th at 3 p.m., we have an e-demo about NVIDIA Grid. Now, it's a great presentation. If you've ever heard about the grid and you've heard that tool being thrown around, well, what's this NVIDIA Grid? We're going to have a presentation about using SOLIDWORKS from the cloud using NVIDIA Grid VCA. Well, I'd like to thank you guys for attending. I have my info here. This is my email, my direct email, as well as my direct line for analysis consulting. If you guys have any questions about analysis consulting, mentoring, or this webinar, feel free. Myself and Jared will be on the line for a few minutes after here to take any questions that you have. We are going to be posting this recorded webinar at this website, hawkridgesys.com/events/recorded webinars. If you came in late or you want to show this to a colleague, we'll have it posted there. And then, as usual, our main line, if you want to contact tech support, 877-266-4469 in the U.S. or 866-587-6803 in Canada. But again, thank you guys for attending, and have a great rest of your day.